Okay, thank you, David, for the introduction. And thank you very much for the visit here. I mean, I would like to thank you and the center and physics department for partially also supporting the visit. So I'm quite happy to be here. And while coming here, I mean, I took 1 hour from my hotel. So I saw most of Lisbon. So, okay, yesterday. So that was quite nice, interesting. So this is, yeah, so I'm going to talk about this time delay interferometry. I mean, this was a technique which was introduced by the people at JPL, actually. And they did it in a certain way. And what we found later on that this is, in fact, connected with, I mean, this is exactly the problem in mathematics, in algebraic geometry, and which was actually posed by Hilbert in 1890. Okay, that is the thing. But the problem was so hard that it was solved about 80 to 90 years later by Grobner and his students, actually, in the 60s or the 70s. And so that's what I'm going to use for, I mean, show how this works and pose this problem in terms of this and how it can be solved quite elegantly in terms of this algebraic geometrical methods. So first of all, yeah, let me say that this is like an eclipse. Okay? So this is a CZG. So I'm going to talk of the module of CZG. So a module is a structure, over a ring. You may have heard of vector spaces, which is vector spaces are, abelian groups over fields. This is a abelian group over a ring. Okay, so that's a module. So this is what was introduced by Hilbert in 1890, and he called it the module of CZG. And why CZG? So he took that word actually from astronomy. This is a CZG. When you have eclipse, you have a CZG like this. It's basically a linear relation between objects. So there, his linear relation were polynomials in rings and so on. But he used the same word. He just borrowed it from astronomy, and we are back to astronomy now, using his module of CZG. So anyway, that's the sort of connection which I wanted to say, and I'll probably it will become clear as I go on. So ground-based basic interferometric detectors, they are in all operation now. So have taken great strides in the past, not few years, many years now. Okay. About 90 black holes, neutron star binaries have been observed in masses ranging from neutron star masses to almost 170 M-sun. Okay. In the run 01, 02, 03 of the LIGO and the Virgo detectors, and also now the Japanese detector has joined it, Sagra, into this thing. So, and there is the fourth run, which is still going on, and many more have detected, but those are not yet confirmed. Those are just alerts. So probably another 100 more, okay, can be added to this. So there are a lot of these things which are there with the ground-based detectors, but they can detect, this kind of black holes and things like that in this particular range. But the reason for this is that these are high frequency detectors and they operate in the 10 hertz to few kilohertz. That for 10 hertz, of course, right now we are not at 10 hertz. Right now we are like 20 or 30 hertz. That's the bandwidth, that's the lower end of the bandwidth of the detectors. And it goes up to kilohertz, okay, in this thing. And because of this puts a bound on the masses that you can detect. You can't go above certain masses because they will coalesce below 10 hertz, the frequency. So the bandwidth with this and the band in which you detect is always detected with this. But the thing is that there are a lot of interesting sources in astronomy. I mean, which would emit gravitational waves below 10 hertz. And the reason why you can't go below 10 hertz is because of basically gravity gradient noise and the seismic noise, which is there in the detector, which is hard to eliminate below 10 hertz. Okay. So the solution is to go into space. So that's why you have the space detectors. And then the sources are different. Okay, here's a global network of here. So this is a detector. So you have a global network of observatories, and you need a global network because you want to sort of locate where your source is. Is this any detector which is like the interferometer? Okay, it's sort of omnidirectional. So I mean, you can't given one detector, you can't say from where the wave is coming. It's like a dipole in radio astronomy or something. If you have a dipole, you don't know from you might detect something, but you don't know from where the wave is coming. So it's something like that. So you need detectors which are separated by several wavelengths or something like that, and which will tell you that you can do time delays or you look at the time differences. And from this time difference, you can triangulate where the sources are. If you have more than something like 3 detectors or more detectors, the better. Then you can get a better estimate of where the location is. So there's the LIGO, LHO, and all that. This is the Hanford, and there's a Louisiana. 2 detectors here in North America. Then there's a Geo, but this is too small to detect anything. Then there's the Virgo detector, which is in Italy. And then there is the Kagra detector, which has just come into whole network, which is now, I don't know what's the range right now, but it's around the megaparsec, it's not too much. Well, these detectors are gone into about 160 megaparsecs, 170 megaparsecs, and so on. So that's the sort of range. I mean, I think people would know megaparsecs. Yeah, okay. So this goes up to 150 megaparsecs, 170 megaparsecs, and so on. So this is still in the, I mean, improving the sensitivity day by day, getting there. And then there's LIGO-India, so which is a detector which has just started work. I mean, started to build this. So just basically the simple work is done, and I think they'll soon start putting in the pipes and all that for the whole interferometer. So that's there, very close to Pune, where I am. Not very close with in relation to the size of India. It's about a few hundred kilometers from where I am. And actually, I was the first in the team to go and see the site. I mean, select the site actually. I mean, there were several sites, but of course, I mean, there are so many competing sites for this. Finally, by some chance, this was the site which was selected. And in fact, I mean, when I went there, I was very impressed by the site. So, because I thought that this would be the perfect site for a ground-based detector because nobody is there. So then you can't have noise. It's the best place for this thing. Okay, so we go to space detectors. So why go to space? The basic thing is that ground-based detector, there is a, as I said, below 10 hertz, it's very hard to detect sources or remove the noise below 10 hertz. And so the solution is to go into space. And there you don't have, of course, this big noise, the earth does not vibrate and so on. So there you have, if you go to space, of course, there are other noises which come in. And these will look at sources in the range of 10 to the minus 5 hertz to 10 to the minus 1 hertz. And I will be restricting myself to LISA, but the same thing applies to also other space detectors with more complicated topologies. So LISA is the kind of thing which I'll take as the main thing. There's a laser interferometer space antenna. So this is planned in the next decade. I have not put the year because I don't know, it keeps on changing. So I think now the last I heard it was 2034, but I don't know. So, and it's possible that the Chinese might put in a year earlier. I am not sure. Their detectors, of course. So there is one source which plagues the detectors, the laser interferometer detector, and that is the laser frequency noise. And the reason for this is that it is an unequal arm interferometer. You can't keep the length of the arm the same because these are spacecraft which are orbiting the sun. Okay, and they are on geodesics or freely going particles, but they are at such points, they are almost, the distance is almost kept the same in this thing. And, but they are not, the length of the arms are not equal, basically. And if they're not equal, this laser frequency noise does not get cancelled. In a ground-based detector, you can do that because that's more under control, and you can do this kind of thing to keep using beam splitters and so on. You can do this kind of arrangement. So here, this laser frequency noise is also there in ground-based detectors, but you can cancel it because you just make the arms as equal as possible. Okay. So laser frequency noise is much greater than other ambient noises like photon shot noise, acceleration noise, all sorts of noises are there in LISA. And so this noise comes from the laser. The laser frequency is like 3 to 10 to the 14 hertz. It's a medium wave laser. And the frequency noise is about few tenths of hertz per root hertz. Okay, so that's the sort of thing. So if you take the ratio, delta nu or nu naught, this is the sensitivity. I mean, you get few times 10 to the minus 14. Okay. But the kind of sensitivity you need is like 10 to the minus 21, okay, for the sources which you want to detect. This H is the metric perturbation. So you write G mu nu as, say, you take the flat background, eta mu nu plus H mu nu. A typical component would be this H. Okay, this thing. So you need to go to H to the minus 21 if you want to detect, say, supermassive black holes or things like that, which are the kind of sources for LISA. Okay. So as you can see, this laser frequency noise needs to be suppressed by order 10 to the 6 or 10 to the 7 orders of magnitude if you want to get to the sensitivity. Okay, so this is the kind of thing. But the other ambient noises, photon shot noise and so on, is quite at that level, basically. That's where you want to get to, and so it is important that you cancel this laser frequency noise. So this has been a problem. I mean, this has been a problem since people thought about this, and probably right from 1890s or wherever it was thought, not in the 1990s, 1980s or 90s, people thought about space detectors. So let's come to this thing. So we have an unequal arm interferometer, okay? And you have, if the arms are equal, there's no problem. This noise is automatically cancelled. But because this spacecraft, the interferometer is made of, I mean, I don't know, I skipped a slide or what? This is, okay, so this is the LISA triangle, which I'm showing here. This is the orbit of, this is the sun, okay? It goes around the sun and it rotates as it goes on. And these are the individual spacecraft, and you form a triangular interferometer, many interferometers, like 2 or 3. So this is, but the point is that these arm lengths can keep changing because they are on orbits, free orbits going around. And you arrange the orbits in such a way that the arms are as equal as possible, okay, as they don't change too much in length. And that's possible. There is a particular set of orbits where you can do this. Now, and because of they are freely floating, you can't keep the arms exactly equal. So you have to do something else. You have to cancel this laser frequency noise. Yours is a million times larger the noise than the other noise. So this is what you do in an unequal arm interferometer. So you have a phase phi 1c. So L1c is put equal to 1. Okay. For any relativist, c is 1. Okay. So this is the kind of thing which is there. So this is t minus 2L1. So L1 is phases and 2L2 minus phi t. But then the thing is that if you have a thing like this, then you can write this. So this was one of the things which we did. I mean, to write this in operator form. So you call this time delay operator D1 and D1 square minus 1. So this was our notation, okay, which was my notation. I don't know. That's the thing, sort of thing we put it, and that's why the polynomial ring and all those things came in. So D1 square minus 1 over phi t minus 1 into phi t. Phi 2t on the second arm, the L2, is this. And if you take delta phi t, and if the L1 and L2 are not the same, this is not zero. Don't cancel the laser frequency noise. But if you take a combination like this, x3 equal to phi t1 minus L2 minus phi t1 and phi t2, so on and so on, what you're doing is to send the beam like this and then send it round like this. The other thing is you send it round like this and then send it round like that and then interfere. If you do this, you get this combination. Okay? You go several loops in the thing. And if you do this, you can see what's happening. You get d2 square minus 1 minus d1 square minus 1, and it cancels. You can see that since this is this polynomial, which are there, you can think of this as polynomials in d1 and d2. This is commutative, and you could see this thing. This is just what is called the LCM. I don't know. That's what we said we called it in India. I mean that I don't know. Lowest common multiple here. So what you finally get is these two are relatively prime, and if you take the LCM of relatively prime polynomials, what you get is the multiplication of the polynomial. So relatively prime means the GCD. You calculate what is for what is the GCD. I mean, this is actually elementary school math. I think I had big example on it as well. The GCD is 4. That is the highest common factor or the greatest common divisor. 4 goes into 8, 4 goes into 12. But numbers like 7 and 11 are actually right, but maybe 8 and 27 is not right. These are relatively right, because there's no common factor between them. So the LCM is the product, while the GCD is 1. So we have to essentially we have to do this kind of. So this is that's time delay interferometry. Physically, what it means is that we want to make the path equal in length. That's all you need. So that's physically that's what you want to do. And so here we have used basically time delay interferometry in order to cancel this interferometry. It's a very simple thing. But now you come to Lisa and the thing gets complicated. Okay. So in principle, this is this problem. But because you got this triangle and all sorts of complications, it's technically difficult. In principle, it's the same. I mean, so you're doing just this kind of thing. And the LCM is step 2 or whatever. So you want to find the LCM, or polynomials. That's the thing. So what you do is, what you end up with things like this, that you need a machinery, okay, to do this kind of thing. So what you have here is this operators here, which I wrote here. They are now more operators. So you take the simplest model of Lisa, where you have arm lengths which are unequal but static. Lisa, that means the arm lengths don't change in time. Okay, that's the simplest model. So you solve for that's like a 0th order solution. Okay, which you want to find. So if you want to do that kind of thing, you come up with at least 3 arm lengths. Okay, so that's why you want to go to 3 letters. Instead of writing D1, D2, D3, I'm writing them as XYZ because it is, I don't have any suffixes and superscripts and subscripts and things like that. So this was a problem which was can be converted into this. And there is a paper by David Hilbert, the theory there, ambulation formula. David Hilbert, 1890. Okay. And he defined a CZG. I mean, so your polynomials, say, 3 variables, so that F1, F2, Fn. They're all polynomials, say 3 variables, X, Y, Z. Then, what are, and if you write G1, F1 plus G2, F2 are there solutions G1, G2, Gn, which means 0. So this is called a linear relation, as you can see. And this is called a CCG. So this G, by all vectors, D, yes, these belong to an ideal. It's called ideal and so on. And I mean, each of them, yeah, they generate the same ideal, and this is called the module. And this belongs to a module of physics. I'll come to that. What it means. Okay, so this is the mathematical structure which one is interested in. So this is the machinery. So as I said here, this is the machinery of rings, ideals, and modules. And he was interested in for a completely different problem. I think that was the mathematics of the thing. And so, what are rings? So rings are here. There are two operations. I don't know, people must have done this long time back. Plus addition and multiplication, Z, Q, R, C. These are ring of integers, ring operation. This is the field actually, R, C. These are all commutative rings. Say n cross n matrices are non-commutative rings. Okay. So this is, I think, so these are commutative, these are non-commutative. QR, C are fields. That means there are multiplicative inverses inside this thing for except 0. And these are fields, but not Z, the integers. That's not a field because 2 doesn't have an inverse. 2 is a half does not belong to Z. Okay. So these do not have multiplicative inverses. So Z is not a field, but these 3 are fields. And polynomial rings are polynomials in, say, one variable x. So the polynomials in x. And these are the kind of things we need because those operators or the loops and so on, they'll form, you can think of them as as polynomials. And you will add these pieces together, and so you get a polynomial. Each loop and so on will be one term in that polynomial. So Qx, okay, is the polynomial ring in the variable x, like, but where the coefficients are in Q, that means they are rational. Okay? And Rxy is polynomial into in xy, all polynomials in xy with coefficients in the real numbers. Okay? So this is what Rxy is. Cxy is similarly complex numbers. But now we have 3 variables, x, y, z. So these are polynomials, these are all polynomial rings, and one can verify the things for this. So important concepts for this talk are that there are ideals. They are called ideals. If you have a subset of R, then if U is an U and R is an R, it's closed much more complicated. It's closed much better than a subring. I mean, you could have a subring which is a subset and itself with a ring with the same operation. Then that's called a subring. But ideal is even more close. If you take an element outside the ideal and multiply by an element in the ideal, it still gets inside the ideal. So, an easy example is if you take the ring of integers, okay, so all integers you take, that's a ring, and take even integers, okay, that's an ideal. Because suddenly it's a subring because you take, you add even numbers, you get even number. If you multiply even numbers, you get again even number. So it's closed, certainly. But if you even take an outside thing, like an odd number and multiply by even number, it's still an even number. So it gets inside the ideal, okay, inside the set. And such a thing is an ideal, all multiples of 3. So the ring is, there is a kind of special ring. It's called a principal ideal ring. Any ideal, so that's an ideal. Even numbers form ideal. Multiples of 3 form an ideal. All multiples of any integer will form an ideal. Okay, but these are the only ideals in this. They are always generated by a single element. Okay, so these are called principal ideals, and Z is a principal ideal ring, and it is ideal for giving to children. Okay, and they can do all this LCM and HCM and GCD and all that very easily because it's a principal ideal ring. The unfortunate thing is these are not. Okay. So not this. This is fine. This is still a principal ideal ring because Q is a field. And if you have simply one variable, it, everything goes through. Again, all ideals are principals. You can divide one polynomial by another and so on. But RXY is not. This is not a principal ideal ring. And things start getting complicated. And it's not just a complication which is twice as bad, it is 100 or 1,000 times worse, okay, than QS. And that's what Hilbert had to contend with. Okay. So those were the kind of things. If CXYZ is worse, we have 3 operators or something. It gets even worse. And so you get common divisor, LCM, common multiple, and so on. And what we have is we need things like polynomial vectors. Okay. So what are modules? Modules are like abelian groups over rings. Like vector spaces are abelian groups over fields. But these are not so well behaved modules because they are over rings, because there are no multiplicative inverses. Vector spaces always have a basis. Modules don't have. Okay. And so what we need for Lisa or this thing here is something like a basis, but those are called generators of the ideal or of the module. So they don't form a basis because they are not linearly independent. So you might say, why not knock off one of them? Okay, because it's of the thing. But if you knock off one of them, you don't span the module. But the important thing for us is to span the module. Okay? And so these are the kind of things which are there. So here is a Lisa triangle which is there. So here are unequal arms and all Li are unequal. The current thing is Li is something like 2.5 into 10 to the 6 kilometers, is like 8.3 seconds of light travel time. And you name these streams as U1, U2, U3, V1, V2, V3. You take U1 is where is U1? Yeah, U1 is this. It goes for spacecraft 3 to 1. Okay. So that's you send a laser light there and measure the data. You mix it with another laser on spacecraft 1, and you get this data stream U1. Similarly, you get U2, which is here, and U3 is like this. U2 is from 1 to 2, 2 to 3, and so on. And V1, V2, V3 are the other way around. Now, given these things, now there is laser frequency noise in this. You want to cancel that laser frequency noise. So, how do you do this? So, this is the thing. And these are the data recorded as fractional Doppler shifts. You need Doppler shifts, then you take them as frequency shifts. In our ground-based detectors, normally it's phase. Delta phi is taken here. But here the point is that the wavelength which you're going to measure is of the same order, same size as the size of Lisa. In ground-based detectors, because you go up to kilohertz and so on, the wavelength is always much greater than the size of the detector. So what happens is that the phase of the wave does not change when you go from one end to the other end of the detector. Okay, in ground-based detector, 4 kilometers is much smaller than say 300 kilometers. Suppose you take a 1,000 hertz wave or kilohertz wave, the wavelength is 300 kilometers, and the phase does not change. But that doesn't happen in Lisa. In Lisa, the distance is like between the spacecraft is 2.5 million kilometers, but the wavelength could be of the order of the same, a million kilometers or things like that. So you cannot use that, and so one will have to integrate the metric perturbation along the null geodesic, okay, from one spacecraft to the other. So integrals are hard to deal with for the phase. So you simply differentiate it. Differentiate the phase and what you get the frequency. So that's why you get, this is a much better observable to use. Delta the Doppler shift, delta nu I or nu naught. Okay. So these are the things, and one such data stream can be written down like this. In C3 U1, for example, can be written down as C3 T minus L2 minus C1, plus there are extra things which are coming. But I am only we're going to concentrate on the laser frequency noise. So these are the laser frequency noise terms, and that is what I'm interested in. So then we have gravitational wave signal, optical shot noise, and so on, acceleration noise, proof mass noise. But these are all small, so we have not bothered about that. So here, so we use the algebra of finite differences, dk, where d of a function ft, dk is f of t minus lk. That means you just relate your data, okay, by the time L1 or C, L2 or C, and so on, things like that. So those are the operators, dk. So then you can write U1 as D2C3 minus C1. This is D2C3 minus C1 and so on. I don't care about the other terms, so I have not written them. And V1, V2, V3 are there. So these are all only laser frequency noise terms. And those are the ones which we want to cancel. So remember the earlier one, I mean, where you had these loops and so on, where we had D1 square minus D2 square, and so something like that we need to do here. Okay. Except that this problem is technically much more complicated. And that's why you need algebraic geometry. So this is a general data combination where you take sigma I, you combine all the data streams together. So Vi and Ui, but you can multiply this by a polynomial in the delay operator. The delay operators are D1, D2, D3, and they are polynomial Ei and Qi. And in the simplest form, this ring is commutative. That is when the static, we take the zeroth order kind of thing. So the laser noise cancellation term thing, I mean, condition is Ei, Vi plus Qi, Ui equal to 0. Exactly like this. So that's where the CZG comes in. That this is a linear relation, okay, with the D's and so on. It's a polynomial thing. I explicitly write down those things. So one solution, you might think, does it have a solution at all? So one of the things which has been written down by all these people in 1999 or 1998, Armstrong, Easterbrook, and so on, was this solution, zeta, okay? And which in our notation, I mean, the way they wrote it down is completely complicated. I mean, it's not so easy to see that. But in our notation, it looks quite simple, just this. D1, V1, D2, V2, D3, V3, and so on. And if you look at this, open it up with Vi and, this other earlier thing here, these things, you get a identity actually here. So whatever function C1, C2, C3 you choose, this is here. Okay. So this is just open this out. Okay. And it's automatically filled. Okay. So this is a combination which cancels the laser frequency noise. You might say, what happens to the signal? The signal gets a bit turned up, but it doesn't get cancelled. That's the important thing. The signal should not get cancelled by doing this kind of thing. So, but this is not so useful for detecting gravitational waves because this really cancels away. It's too symmetric, actually. You can see this kind of thing. And so it partially sort of cancels the signal, but it is still useful for things like if you want to look at instrumental noise only. And now there is a thing that there is a confusion noise of white dwarf binaries in our galaxy, which might which might give a sort of a noise at lower frequencies than LISA. Okay, and this kind of combination can be useful there because it will cancel the gravitational wave signal there. Okay, so anyway, so that's not my talk actually, but anyway, I just said that. Identify arbitrary function, and so this is a solution, and we write it like a polynomial vector. So this is a polynomial here. 6 polynomials, like, but they are very simple polynomials. They're just D1, D2, D3. Another solution which was given again, Armstrong, Easterbrook, Tinto, okay, around that time, and which in our It was called the Michelson. It's exactly, you leave out one of the arms, the interferometer. Just take two arms. Then this is the combination which cancels the radio frequency noise. Okay. But then in this kind of thing. So now, how does this thing come? Is yeah.
How do you implement this signal combination?
Yeah, so in practice means that you take the data and delay it by the length of the time delay.
So it doesn't matter. You need to combine the signals physically in one place.
Yeah, no, so you measure data, yeah, the signal data is, there are 6 data streams which you measure. You get 6 data streams as your input. Yeah, you do it offline. So you don't combine it offline, means you can do it on there also. And that's one of the things which we suggest here actually. There are 4 generators. You don't need to send 6 streams. You can send just 4. But that's what I'll come to at the end of the talk. And so this is one combination. But how does this come? You can formally write down this equation. So for the CI, there are 3 CI, you get 3 equations. C1, C2, C3. You get P1. So if you put it back into this kind of thing, P1 here, and then put this back into this kind of thing, for each C1 and C2 and C3, C1 you get this, C2 you get equation, for cancel C3 you get this equation. So all 3 equations have to be satisfied by the polynomials in the operator. So this is each of them is a CZG like. But the point is that you can eliminate, there are 3 equations that you can eliminate P1 and P2. It leads to just one equation, which is more complicated in this thing. And this is exactly again inverse CZG. And he proved a lot of theorems and all that at that time. And one thing which is important to us, and that's why it works, is this, that these ideals or the modules are finitely generated. Okay, so I think there is a theorem we gave. It's called the CZG theorem. Okay, Hilbert's CZG theorem and so on. And one of the things he proved, I think, that all these polynomial rings are what are called Noetherian. That means they're all jargon, but anyway, what it means is the ideals are finitely generated. That means you can choose a finite set of polynomials and build up the whole ideal or the whole module. And that's important because you don't want your algorithm to run to infinity and all that, and then otherwise you can't do anything. So, or infinite number of generators. But here you have finite. I mean, that is guaranteed by Hilbert's theorem. So, the rings which I showed you, Q, X, Y, Z, C, X, Y, Z, they are all, it's over a feet. They are all what are called Noetherian rings. Okay. And every ideal is finitely generated. And the module also, which is over that. And that's important for us.
Is there a unique choice for the generators?
No, that's the thing. But so you take the simplest one. Yeah. Take the least number of loops or something like that. I'll come to that. I don't know how much. Oh, I'm going a bit slow, I think. But anyway, I think I'll skip some steps earlier. So we need to solve this for 6 Pi and Qi, P1, P2, P3, Q1, Q2, Q3, or the polynomial vector. This equation, which is a CZG. Now, how do you solve it? So there's a whole machinery, and Hilbert could not do it actually. Even, I mean, this problem was not. He proved that there exists a module. So all these combinations will form a module. So if you take P3, Q1, Q2, Q3, they will form a module over the ring. But so that's called the module of CZGs. He showed that such a thing would exist. But how do you get it? I mean, that means how do you generate such a module? Like a basis, you need something like that to generate the whole module. That he could not do. And people did it in the 60s or 70s. And that's called the Grosvenor basis and things like that. So I'll just quickly go through that. I mean, I don't want to go through all the calculus because otherwise the talk will go on for another 2 hours or something. So solutions are 4 tuples because we have to solve only these. And other ones we can get by elimination equation. So this belongs to K4. K is this ring. We take integer, essentially integer polynomial, integer coefficient. But rational is good enough because you can clear out denominators. And Q is better behaved because this is a field. Okay. So Q, X, Y, Z we take. And phi, you should write K4 to K. This is the mathematics of it. So any P3, P1, Q3 is mapped to this polynomial, which is in K. Okay, that is the ring. Ring is this, okay, Q, X, Y, Z. So what we want to look at is the null space. We want to cancel the noise. And that's why you need the kernel of this mapping. That all those elements which map to 0. Okay? And that's what you want. So solution space is this, the null space. Okay. And null what? The null in noise. The noise has to go. There is a noise. And this is called the first module of physics. This was the what Hilbert called the kind of thing. And you can get the entire thing by elimination equation, and you get the 6 things here. So that's the thing to do. Now, how do you do it? Is the thing is that generating the first module of physics. How do you generate it? And this was the method. Obtain what is called a Grobner basis for the ideal U, generated by the coefficient. So the coefficients were here. These are the coefficients. This, this. These are the 4 coefficients. And so they are here, here, okay. And you find you have to go to what is called the Grobner basis first. So that's the first step. And you choose what is called the lexicographic order, okay, this thing. And if you do that, and there's a whole machinery, I'll just flash slide how it comes. The Grobner basis turns out to be, it's like a GCD, like 8 and 12, the GCD is 4. You are taking a GCD instead of the polynomial. You have to go down so that you can generate things you can divide. And this is, in fact, what is called the Grobner basis. You get the same idea as this. I mean, these 4 elements generate the same ideas in Q, X, Y, Z as this one. But these are sort of down, they are lower, like 4 is less than 8 and 4 is less than 12. There is a certain order you can put on it. It's a very simple order. You put, see the point in this rings is that you take a ring in XY. Suppose you take 2 polynomials, x squared plus y and x plus y squared. You can't say which is greater and which is smaller, okay, a priori. Like if you have a polynomial in one variable, it's okay. You just take the degree. X cubed is greater than x squared and so on. It's obvious to do that. But when you have polynomials in several variables, that's the problem here. Here you have 3 variables or something. It gets worse. You can't really define an order and you have to put it by hand. So this is one of the orders. We choose this order. Okay. So this is the lexicographic order, it's called, okay, in the literature. And that gives you these figures. I will just give you how it comes out. Form matrices, this is the machinery. Okay, this is all the way it goes. See, the theorem guarantees that the full module is generated. And the above procedure generates the 4 people generate this, and then you get the. So this is these are the steps. So first get the Grobner basis, and then you go from Grobner basis to the module of physics. So I will just flash those slides because there's no time to go through that. So here is the thing. So this is F1, F2. Next gives you, it's called what the logarithm is. This is the biggest polynomial. Okay, because what you call is x square is the head term, is bigger than 1. You take what is called the logarithm. So x is greater than y is greater than z. So you write this logarithm as like this f4 as 2, 0, 0. So this is whatever 1 minus x square. X square is the term. So you just take x square. This is the logarithm of this. And the logarithm, the next one is f1, so the xy z. This is the head term. Head term is that's the biggest one. This is the thing as 1, 1, 1. And then xy z. this for the X, Y, Z. And you look, start from the left hand most. 2 is greater than 1, so Y is greater than 1. That's why this is F4 is greater than F1 and so on. F1 is greater than F3 and F2. And then you kill the thing. You, go down by cancelling head terms. That's the idea. Okay. So these are called S polynomials and so on. So there is a whole machinery how to do this. There is a software to do this, Macaulay too. And I think the global base is also there on Mathematica. Your Mathematica does this thing. You have to give the whatever order or something like that. So you do this thing, and finally you end up with this is the global base. So you keep on calculating this thing until you get to the bottom. And how do you know this is the global basis? If you take the S polynomials of any polynomials here, they go to 0. While here they won't go to 0. Your polynomials are sort of bigger, okay, on the top. They are sitting like this at the top, like 8 and 12. Like 4 sits down. Okay, so it's exactly like that. So like this was also a problem that how do you know a certain polynomial belongs to an ideal, which is generated? You are given, say, certain number of polynomials like F1, F2, F3, F4, and you want to know whether a polynomial belongs to the ideal generated by them. But the point is that the polynomial can have a lower degree than this because things can cancel out. Okay? And that is what you want to avoid. And the global basis is exactly that. It goes right to the bottom, and you can divide any polynomial by this. So if you here it was simple. 4 divides 8, 4 divides 12. So you get this. And here the idea of global basis is that you can divide a polynomial like 6, y, z minus 1. I can divide this by taking, say, x minus y, z. But now divide this by a set of polynomials. So if I take this, this will be like y, z will come here. X, y, z minus what is y squared, z squared. Okay. I just multiply this. Plus minus plus here. So this becomes y squared, z squared minus 1. Now you want to divide this by y squared minus. Don't have to take this element and divide this here. So you get z squared. And this becomes y squared, z squared minus z squared. Plus the minus this cancels. You get z squared minus. But that's fine because you take z squared minus 1 is then you simply divide it both here. So the whole thing is this is called the book burger algorithm. It was given I don't know around 70s, I think. How to do this kind of thing. Yeah. Oh yeah. So this is the whole kind of thing which goes around and around. This is the whole kind of thing. And you have to go through this. Given in Becker, there are these commutative algebra books which are there. How to do this thing. And you get this matrices. And you go through this. So I don't want to go through the whole thing. Finally, you come with a set of generators which are here. This is a theorem which tells you that these are the generators. P1, this is the 4 generators. P1, P3, Q1, Q2, something. And so there are 7 of them, but so they are not independent. So you can reduce that to just 4 generally. So you can just stare at them. So you have to go through this whole calculation. And what you get is one set of generators. Macaulay 2 software also gives you this generator. Another generating set which is used very often now is this one. These are called Sagnac combinations. This is what was called by Armstrong, Estabrook, and so on. And there are alpha, beta, gamma. These are Sagnac, and this is called the symmetric Sagnac. There are 4 generators of this module. So what you get is for the Grosvenor basis, you have gone to the module, It has got 6 of these things. There are 4 of them, but they are not linearly independent. They generate the module, but that is what you want. I mean, you want to span the module. You don't care if they are independent or not. So that's the thing with the module. It's not what is called free. If you have a free module, then it's like a more like a vector space, your basis. Here, this is a sort of an entangled module, which Hilbert did like actually. So I did not. So he tried to set them free. So that was the CZG's theorem he proved to calculate another module of CZG. So these are related again by some linear combination. And I'll just say something about that. So module is, and one thing one can say is that these are from above generators to basically read. So these are a preferred set because these are the lowest degrees. Okay, and that is, I mean, depends on what application you are doing. So if you are doing, if you want low degree, it's fine here. Or you can choose a Michelson, which gives you a high gravitational wave signal, pretty high, and so on. And as I said, zeta is useful if you want to cancel the gravitational wave signal a lot and only look at instrumental noise or separate out things and so on. So one thing you can do is, like in radio astronomy, you can use these combinations to get the highest signal to noise ratio, okay, for a particular source. So if you have a source fixed in the sky, say on the equator for the Barrett set is framed, you take theta be equal to 90 degrees and phi be 0, say on the longitude. Then by changing the combination, you try to get the highest, largest signal to noise ratio. So keep on changing the combination because the LISA is changing. In the frame of LISA, the source goes around like a 8, looks like a 8 because the LISA rotates, that goes around. So the source goes like this, but if you take a certain combination of this generators, they'll give you a certain signal to noise. So then how do you maximize this? You can maximize it by using this. So this is what is done also in radio astronomy. If you have a cylinder like this or something like that, you phase delay the dipoles and you do this. So this idea is basically radio astronomy kind of idea. Okay. So you can do this.
Shows the generators for how to combine the signal to kill
Yeah.
the noise,
Yeah.
but then among
Among those, yeah.
have,
Yeah. Maximize the
Maximize.
signal. Yeah. So in each direction, it has a different response. These combinations. So you take the best one. And because the LISA is rotating, the source, although is stationary, in the LISA frame, it looks as if it's rotating or it moves in a different location. So you'll choose a combination there to do that. So that's one of the kind of things.
So by knowing the evolution of these, say parameters to get the best signal to the you can know the direction in the sky.
Sorry.
So as I,
yeah.
if I understood properly, Lisa says here.
Yeah.
Then you need some
Yeah.
combination. And then it changes and you
Yeah.
need another
Yeah.
combination.
So you can find the location.
So you can find
Yeah.
Okay.
So that is a thing which can be done. So it's like having many interferometers or something because it's changing with orientation all the time. So not only location, polarization also. Both. So this is the thing, but this was the simplest model. The point is that actually the arm lengths are changing. Also, the LISA is rotating. So there are other effects which need to be taken into account. But there are perturbations on this solution in a way. So light travel time around this way is not the same this way because the LISA is rotating. So the arm lengths have to be not 3. So you get 6 delays. So your polynomials are more complicated, 6 variables. And also the time dependent arm lengths are not independent of time. So these operators don't commute, so you don't have a commutative ring in general. So, but the point is it almost commutes because the arm lengths are changing very slowly, the way the things are chosen. So you can take, if you cancel the thing in linear in velocity or L dot, you can say, you're okay. I mean, with Lisa. One thing gets left module, but apparently uh, this solution, I mean, I've been tried a lot, but we couldn't get anything. But apparently there is a Chinese paper which says this is a zero module. There is no module at all. Actually, there are no combinations for the general problem. But approximately you can solve this thing. So there will be some noise, and that's good enough. You make a Taylor series expansion of the operators in this thing. So one of the things is this approximate solutions of just by taking commutators of the operators. So if you do this kind of trick, okay, you can obtain a lot of solutions for Michelson kind of combination. That is, one arm is not there. So we do this paper in 210. Okay, this is one of the things there. Then second generation time delay interferometry. So the first generation means the static one. The second generation is the time dependent arm length. You can lift this combination without simply perturbation to other things using nested commutators. So you use commutators and all that sort of thing to cancel the noise. Was 220 dollars. So the Tinto was is one of the collaborators, and we wrote a review article in Living Reviews, Tinto and myself. So 221 is a Living Review article on it. Then higher order time delay interferometry, you can also go to even more nested computer and cancel noise at higher orders. But that is not needed for LISA. Just velocity is enough. But there could be other space detectors where the arm lengths are changing more rapidly. In that case, you can also do this. And this was one of the things how we have shown how to do this. And there were other things, matrix formulations of TDI. So you can write this operator in terms of matrices. So these are essentially representations of the operators. Okay? And the matrices are inherently non-commutative. So time delays and all that fit quite well into matrices. So it's a very good idea to do this. But the point is that they are representations. That's one of the, there's nothing, it's not new. So there are all these papers which were written. And the TDI infinity by Valisner et al. By people in JPL and so on. And we also wrote a thing, all kinds of integral and so on. So anyway, that's the detail. So results. So this is the last slide because so we have a general method for generating all the data combinations for canceling noise, even for time independent arm length. So that is mathematically, but the theorems guarantee that. And method can be applied to more general configurations, and it has been applied by several authors. I mean, Wang, et al., I think 230. These are follow-on missions. There is a much more complicated set with octahedron. Okay. And there are 24 links to this thing. Instead of 3 links or 6 links of Lisa. And they have shown this thing. Optimally track a source. You can optimally track a source using this thing. So you can improve the sensitivity of Lisa by doing this. And then the mathematical thing is Hilbert series. Hilbert is also satisfied. So because of the Hilbert series theorem, module was resolved with the atmosphere. So thing is that if you have a polynomial ring in n variables, then this module of CZG resolves. You keep on taking CZG of the CZG. That means the generators are not independent, as I said. There's a linear relation between the generators. And those linear relations form another module. That's got the second module of CZG. Like, it will be, okay. So here is the, and it resolves, means that it becomes free. You get a free module at the end. And Hilbert always wanted free modules because they have good properties. Okay. So was resolved at 3 steps. Here we have the second module of our series is free in the case of Lisa. And we have 3 operators, so it's satisfied in 2 steps. So at most, so it could have gone to 3. Then I don't know what is the physical significance of this. I've tried to figure out. This is not as entangled as other modules. It is closer to real. There is only a generated by the polynomial vector like this. So this is a canonical basis. So I don't know whether that. Yeah, that's it. So okay. Yeah.
Was thinking about well, like
Yeah.
How equal, like what is the
How equivalent the ground base?
yeah, give example like how what kind of like frequency then so that this kind of
Okay. See here it's like 10 to the 6 orders higher. I think it's the same for ground base. So you need to have it within millimeter or maybe something like that. Millimeter or something, or millimeter or yeah. So 4 kilometers into 10 to the minus 6. I don't know how much is that. So it is like yeah, probably a millimeter. That's the kind of thing in ground based. And here we can't do it. Even it's a 2.5 million kilometer arm length. You 1 millionth or 10 to the minus 7, 250 meters or something like a kilometer. So if your arm lengths are smaller than that, but it's not that, it's the number of loops you make. So what it does is it puts what you call upper bound on the polynomial, the degree of the polynomials that you can use. That's how many loops you can make. Otherwise, it should be the number of loops. Arm length changing should not, the change in arm length should not be more than this 1 part in 10 to the 7 or 1 part in 10 to the 6 of the total arm length. So maybe a kilometer or something. So, and the rate at which they change is like few meters per second for Lisa. So in one, this thing which is like 8 seconds, it will move like 50 meters. I don't know how much, 50 meters or something like that. So probably if it is like, you can't have a polynomial greater than 20 degrees. I mean, whatever. 20th degree polynomial or 15. But you don't need to go that much. Yeah.
So you explain that noise the laser noise cancellation can be achieved by or can be rephrased as constructing an operator
Hmm.
such that it can now listen to.
Yeah, that's right.
And we could find such operators in the case of time independent on.
Yeah.
My question is the marginal phase of time dependence.
So you can't find such a module.
But does sort of theoretical.
But here it's not exactly. It is these are I mean this is an approximate solution.
My question is it's well, before that. Is there an theorem that guarantees that such an operator exists? Does the problem have a solution?
I didn't understand what.
Is there any theorem?
No, I don't know. I don't know that. I don't know such a thing. And this has actually been shown by Chinese people just a year back or something. And we didn't really realize that. I was trying to find for the non-commutative case that this is they proved it that it's a zero module or something. I'm not sure of the proof of actually. There's no non-trivial solution. That's what they claim, but I have not looked at the proof very carefully. Or they say it, just say it or something like that.
That's the case. The next best thing is to find an optimal. The one that reduces most of the noise, you want it to be below.
Yeah, so that's what is done here. So I mean, noise is not completely cancelled. It just suppressed below the other ambient noises. with this kind of thing. So we are satisfied if it comes less than the short noise of the acceleration noise. The acceleration noise is the one which comes because the proof mass is in the center and out. And suppose this proof mass was there, it will get bombarded by say, light and other things, say from the sun or cosmic ray particles or whatever. And so it will move because of that. But then there's a drag-free technology where you cover the mass with the shield, this thing. But then the outside shield gets moved up and down. But you lock the shield onto the proof mass. That is what called the drag-free technology. Okay. So then but still there is an error. I mean, which occurs in this thing. And because of whatever, I mean, yeah, it's a technological thing. And you still get some noise. That's called acceleration noise. And this thing shows that we can also cancel that actually. But it doesn't need to be for Lisa. Yeah, sure.
If I understand correctly, your machine tells you that the noise to zero, but does it tell you what's going to happen to the gravitational wave data on the same?
Oh, yeah. So gravitational waves, the signal is not cancelled.
But does it,
Hmm?
you mentioned that in some cases it might.
Yeah, so I mean, it depends on combination to combination. I mean, if I go back, the least sensitive to signal is this combination. The theta is very symmetric, as you can see. But these are quite okay. But the best is the Michelson. This one is Michelson, I guess. The 0 here. So this is the Michelson combination. It basically uses two arms. Okay. So that is the best one to signal for the signal. So normally people use this for pairwise. You take these two, 1, 2, 2, 3, 3, 1. And these are the kind of things which are used, I think, for example, setting bounds as a stochastic signal or something like that.
So it's basically treating the detector as three separate detectors.
Yeah, that's right. So, but they are not independent. These noises are correlated again. So you have to be careful. You have to diagonalize the matrix. So that is also done. I mean, and then you get three combinations. But the problem with that is that they don't span the module. So what that means is if you take Fourier transforms and so on, you get zeros in the denominator. This is very bad. So, but you use these four because you're using only three. You use four of them. This is I mean, this is what do you call it? Absolutely not smooth. What do you call it? This is, yeah, I mean, you don't divide anywhere. Okay. So, it is a seamless, you can say, seamless solution. While the way they were doing it earlier, they took Fourier transforms as operator. You can solve those equations with Fourier transform, but they are not, you can solve at certain frequencies, but not everywhere. So there are singularities in the statistic. And generally, if there are singularities in the statistic, I mean, statisticians call it wrong. Because if you have singularities in a statistic, that means you have to search for another statistic. But this is that one. So then here there are no singularities, but you don't divide. There's no question of singularity. Okay.
If you enjoyed the video, like and subscribe.